configuration file if it lives in a, you know, a shared space somewhere. But yeah, I wish I was more familiar with the ROS packages in general. That's kind of what I'm trying to come up to speed on right now, is which way to go on some of those types of things myself.
So you think like the joystick package would be it's a small enough kind of isolated package where we could kind of learn and talk about how we set these things up. I don't know, kind of using it sort of as like a learning tool, maybe even put a GUI on it so you can see the configuration. I guess using that as like a little teeny package to talk about what you can do. It's really powerful what you can do with it. You can configure it to do a lot of different things. But starting simple and then working through what you can do with it.
Right, yeah, for sure. Is it, do you have it posted on Git somewhere, or on like GitHub, or is it publicly or privately shareable?
Yeah, it's out on the Ross Agriculture GitHub. I'll post the link here. It's called Tractor Teleop.
Okay.
So it's a very simple, right now, basically just listens to the join node, your joystick, as it's publishing into ROS, and then it reads the join node and then will publish the command velocity messages. And I do have the e-stop button on line 30. Maybe I can share my screen.
Okay. You said you weren't reading engine RPM on your engine too?
Not yet.
I wonder if there's some easy way to get you.
I was looking at putting a Hall effect sensor on the top of the engine to measure the flywheel.
Yeah, I was thinking more something easier, like some type of a buffer, and something that you know, got triggered by a transition in your spark plug wire.
Yeah, if I don't know how to measure the RPM on the engine, or what's the signal to say that the engine is running.
Yeah, I mean, I can think about it a few different ways. The first thing would be, I can imagine you wrap another coil of wire around your spark plug wire or something like that, and then use like a Schmidt trigger to make a pulse when your spark plug fires, and then all you would need to do is measure the time period in between pulses, and then that's your, you know, math to the RPM. Would be pretty straightforward.
I would go with Matt's suggestion and use a Hall effect sensor. You can just take some epoxy and glue one inside of your flywheel cover. So as the magnets on the flywheel go around, they just go past the sensor and you get pulses off that. So it's just a matter of wiring your sensor up to your supply and your ground, and then hook the other pin to a input pin on your processor. So as it goes around, you just get pulses off that.
Yep, that could work too. I'm thinking on the, yeah, I guess if there were, yeah, the magnets on the flywheel would probably trigger a bigger pulse. I'm just thinking if it's metal all the way around instead of having the void, what that pulse would look like. Because usually the Hall effects read like metal or not metal, right?
No, a Hall effect actually looks for a magnetic field. The kind of sensor that Matt has is I call it an inductive sensor, and it will actually, if you get it close to metal, it turns on. You get away from metal, it turns off. But a Hall effect sensor actually needs a magnetic field. So as the thing's spinning around like that, it'll give you nice pulses off from it.
So that's still an area of experimentation, but it would be a nice feature to have. We've had some other guys that talk about like when the engine bogs down, they want to be able to give it a little bit more throttle. So that would be another reason to have that RPM measurement, keep constant RPM. So Jeff, I don't know if you found those graphs, or if you want to talk about some of the work you've been working on.
I did find a directory that's got all that stuff in, so I could take a shot at it here. So unfortunately, every time I pull this up, it makes them smaller. It also, I switched to Windows 10, and it's choosing for me what it wants to use here. Let me try it something different here. That's a little better. I'll zoom in a little bit here. And I don't know if this is in the way. I'll drag it up here. So this basically is just showing the fact that I've got an encoder right on the back of the motor, and that's what the orange line is. So
it's looking at your directory when you open up the new window.
Oh. Let's see, how can I do that? Stop share. There, we'll see if this works. And open that with this. Can you see that?
Yep.
Okay, this is just showing the fact that I've got an encoder on the back of the motor itself, the drive motor, and then the motor has about an 18-to-1 reduction to drive the differential, and then the differential directly drives the wheels. And the encoder is currently a 600 line encoder, and with full quadrature decode, I'm getting 2,400 counts per revolution of the motor times 18 reduction gives me around, I think it's 43,200 counts per revolution of that's how many counts per revolution of the back wheel. So the orange line there, if you look on the right-hand side here, that's the scale for the orange line, and the scale on the left here is for the yellow and blue lines, which is the two wheels themselves. So on each back wheel, I've got a gear and another encoder on each one, and that one has 128 line encoders and a 3-to-1 reduction. So that one I think gives me 1,536 counts per revolution of the back wheel. So this running, I believe this is running 10 times a second. I was just simply reading up the values. So for instance, this orange line here says we're turning 300 counts per tenth of a second is what that means. And then you can see the yellow and the blue line aren't tracking each other, and that's because my vehicle's up on jack stands. So as it turns, the differential lets one side turn faster than the other. And if I say put my hands on them to slow them down or something, then they'd get closer together. But this is just one of the first tests after I hooked my encoders back up. I wanted to verify I could read the all three encoders on that. So the yellow and the blue go together with a scale on the left, and then the orange is the scale on the right. And you can see at whatever speed that was 6,000 counts per tenth of a second. And later on I could claim that shows I'm going 1.5 meters per second, but right now that's what that's telling me. So it's just a way to view this as I'd run the speed up and down. And also when I was running forward here, I get these plots that look like this. When I started going backwards, I get all this chatter on here, and I could also hear that. And when I started looking, it turns out my my misalignment coupling that's between my encoder and the back of my motor is actually physically broken. So as I go backwards, it's skipping or something, and that's why it's getting these extra little bumps in there. So let's see if I can do this. Now let's go this way. So this is, I take the recovered position. So those previous numbers that I was pulling up every 1/10 of a second, I just simply accumulate those into a big number. So I've got a 32-bit variable, and I just keep adding those in there. So then as time moves on, I just keep adding. So this is actually the absolute position of how far the wheel or the motor has turned from when I turned it on. So I've started out with everything at 0 over here. I was really confused because well, why is this one off by minus 1,000 there? It turns out, well, you got to look at the scale over here. So the orange one actually, it looks like it's at 50,000 counts. So apparently I didn't start at 0 when I started up this plot here. So technically, when I hit the reset, all 3 counts should start at 0, and as I drive forward, they'll all get bigger, and as I drive backwards, they get smaller. So what else is going on here? So again, it's saying on the left is the axis of the wheels themselves. So that's the scale for the wheels themselves, and on the right is the axis for the motor. And it turns out the motor is, I think, 28 times faster, or 28 times more counts than what the wheels are. So I just have to, later on, I'll show you where I accounted for that. But again, that's just showing you that, and where it says recovers, that's supposed to say recovered with a D in there, but that's, I noticed that after I got it posted, and I didn't go back to fix that. So basically what it's showing is when I hit the reset button, they all start off at 0. If I start driving forward, I just keep repeatedly adding. So we'll take this orange line here that happened to be at minus, well, actually, I guess the orange line is at 0 right here where it started, because if you look at the scale on the right, so the orange line started at 0, and as I start driving forward, I keep adding those. Every 1/10 of a second, I add on how many counts per 1/10 of a second I have, and I keep adding them on. So as you drive forward, that number keeps getting bigger and bigger. And here somebody say, well, gee, that's up to 22,000 counts already, or 220,000 counts already. That's too big a number. Well, so I went through the whole process, and by figuring out the number of encoder counts on the motor and the number of encoder counts on the wheels, the one on the motor, if you feed that into a signed 32-bit number, which gives me plus or minus 2 billion counts, and I go through the whole process and figure out how far do I go with one revolution of the wheel. And somewhere I have some stuff written down, which is not handy right now, but I could show you that. Basically, it turns out that with a 12.5-inch diameter wheel on the back, and you take pi times d, that comes out to like 39.3 inches or something, which is almost exactly 1 meter. So it's real convenient that one revolution of the back wheel moves me forward 1 meter. So that makes it easier to substitute this stuff in and out. So by taking my 43,200 counts per revolution of the wheel, and I know I've got 1 meter per revolution of the wheel, and you take 2 to the 31st, you divide those out, it comes out to 30.8 miles that I can drive before my encoder rolls over. So at one point I was thinking, well, do I have to worry about that rollover? And I thought, well, it's possible I could drive 30.8 miles. You don't really keep track of what you're doing. But then I ran the next equation that said, okay, if I'm running at 1 meter per second and take all those numbers into account, it turns out it would take me like 13.8 hours to get that far. And the saving grace there is my batteries will not last that long. So no matter what I do, when I start off from 0, it's not gonna, the rollover should not be a problem, even though I really should check for it somewhere along the line. So that's what this chart is showing, that if the fact that, another interesting point is my orange encoder is the timer has a 32-bit timer built into it. So I can run a signed 32-bit number, and both the ones for the yellow one and the blue one only have 16-bit timers or counters built into the timer. So what I do is I take the difference every 1/10 of a second. I take the difference from the current value and the last value that I had, and that gives me a delta. So every 1/10 of a second, I get a delta of how many counts did it go in that amount of time. So what I do on the yellow and blue one there, that are only 16-bit physical timers in the count and the physical counters in the timer, I'm repeatedly adding this delta on into just a variable that's a 32-bit variable. So I still get a signed 32-bit number for that. And it turns out the orange one has a physical 32-bit number built into it. So the next experiment I did here was it this one? Oh, I don't think I plotted that one out. So, but anyway, I thought, how can I prove that that's going to work? So it turns out I took the number, the orange line here. This is the fact I accumulated everything back together. So at the top here, it's at 220,000 counts or something. And what I did, I printed out the value right out of the timer. And it turns out those two numbers are tracking each other. So if I drive it for an hour and stop, if I go look at my variable, that's going to match the number that's in the physical counter on the timer. So that tells me that's just a double check to say that I'm doing things correctly. But now the yellow and the blue one, they're going to roll over after 16 bits, which is plus or minus 32,000 counts, and that's going to bite me real quick. So I have to make sure that I go ahead and sum that into another the register I'm using right here, or into the variable, and that's what you're seeing right here. So again, especially the ones on the wheels, since it's 28, I can go 28 times further, 28 times more than 30 miles before it'll roll over with a 13-bit or a 32-bit number. So that should take care of itself. So that's what I did the first night that I was playing around, and I had one more plot here. What was this one? So this one shows right in Excel. I took the left, here, let me back up to that one. So right in Excel, I had all these numbers plotted out, or these are the numbers that every 1/10 of a second it prints out the 3 encoder values. And in Excel, I plotted the 3 values here. And it turns out, you see the yellow one and the blue one aren't tracking each other. But when you do the odometry equations, you add the left distance traveled and the right distance traveled and divide it by 2, and it gives you the average of the 2 values. So even though it looks like they're all over the place there, once you average the 2 together, they come out. So then I went here, this one, and here you can see this is the orange line that we were just looking at. So the orange line comes up, and it turns out since the orange line is 28 times higher resolution than the other one, I just blatantly divided it by 28 and plotted it. And then for the yellow and the blue line, at the top here, it says I added those together and divided by 2. So this scale right here tells me that after however long I drove here, this is how many encoder counts that the wheel thinks I've turned. And the one on the motor itself, the orange one, would normally be 28 times larger, but I divided it down. So this shows me that the encoder on my motor is tracking the encoder on the wheels. And again, here's that chatter down here because of my broken coupling. So basically that was, again, I just started driving forward and then came to a stop, and then drove backward and came to a stop, and drove backwards more and came to a stop. So you can just see as I speed up and slow down there as the thing moves along. So then the next night, let's see, I think this was a steering experiment. I was looking at my, because I put a wire into my super servo so I can read out the voltage on the feedback sensor on that. And that's what the blue line, or no, that's, the blue line is, it says at the top here, I took my joystick and multiplied it by a scale value, and I feed that to the RC servo. And that's what's controlling. As I move the joystick back and forth, that's saying it starts off at this position, which is basically 0, and I move it all the way to one side, and it comes down here a ways, and then I let go of it, and it goes back to 0 again, and then I go to the other direction. So that's what the blue line is showing. And then the first thing I noticed was this yellow line is what I first started reading out. I thought, number one, that's filtered way too much. There's two things that give that away. Number one, it's so curved instead of having nice straight edges to it. And the other thing is it's offset. So you can see here's the square wave here, but this thing is offset by, I don't know however many counts that is. So I thought, well, I must have, because I know I have a physical RC filter on the board right now, and I don't remember what the values were. And then I realized afterwards that still wasn't doing a good enough job, so I had a running average filter running. So I went back when I plotted this one out, and I took the value before the running average. So you can see the orange line is not as smooth as the yellow line, and also it's shifted back to the left somewhat. So it's better, but it's still awfully noisy. And basically what this told me was, I can't just immediately use it. I'm gonna have to go play with it and figure out something else to do here. So it's just a quick test to see if the number coming out was tracking the steering. And you can see it does basically track it. Here you can see the, well, again, I got two different scales here. So the scale on the right and scale on the left means that these two vertically are not lined up. So basically, it looks like it's following it, but it's going to have quite a bit of work done to it before I could actually use it. So that was just in passing, I did that. So then we move on. So then last night, what I did was, so all the stuff I did 2 nights ago did not have any of the odometry equations at all. I've just taken the numbers from the encoders, dumping them to a file, then plotting it with Excel. So at this point, which was last night, I went back in and I took the numbers coming out, or right in the code in the microcontroller. I said take the left side and the right side, and I did the odometry equation where you say add the two together and divide by 2. So see, the gray line is the average of those two. So even though in this case the blue line and the orange line seem to be varying all over the place, you can see the gray line's a nice smooth orderly speed value coming out of the thing. So then I move on to the next one here. And let's see, where is it? This one is that gray line I just showed you, and since I was sampling it 10 times a second, I just blatantly multiplied it by 10, and you can see that with my joystick at full on here, it's running at around 1.5 meters per second. And that's something I'd calculated earlier based on all my encoder values, and when I just hooked the motor directly to my battery and looked at the values coming out, I ran some calculations, said, yeah, it looks like it's going about 1.5 meters per second. And then when I plot this out, it shows that is how fast the thing's running. Now, in real life, I can only run it, say, about 1 meter per second because I need overhead for the motor control. So when I put a PID equation on there, if the motor starts bogging down, I need enough extra overhead power to keep the motor running at 1 meter per second. So earlier when I said, well, I calculated that if I go 30 miles, or no, if I go at 1 meter per second, it would take me 13 hours to exceed my counter. Well, that's where I came up with that 1 meter per second, because at full out on a 12-volt battery, it'll run 1.5 meters per second, but I'm gonna have to control that down to say about 1 meter per second in order to get decent control out of that. Now it turns out it's a 24-volt motor, so theoretically, if I'd run 24 volts, I might run twice that speed. I may be able to run 3 meters per second. Uncontrolled with it connected directly to the battery. But I'm going to try to get by. In fact, I'm sure I can get by running on 12-volt batteries, just I can't run as fast as I might want to otherwise. But it's big enough and heavy enough. I don't want it going very fast to start with anyway. So let me back up here. So again, this is the first one I did last night where I'm showing the left encoder and the right encoder on the two back wheels that are, again, those put out 1,536 counts per revolution of the wheel, and I'm sampling that 10 times a second. And after I added them together and divided by 2, I get this nice gray line there. And then the next odometry equation you do is you take the left side, the left difference minus the right difference, divided by the distance between the two wheels. And at first, I thought, boy, that's really complicated. I'll never figure out what that's doing. But when you look at it, it's really just taking a ratio of a circle. So what happens is the number that falls out of this is just a number in radians, because you say the fact that you're taking the distance between your two back wheels is the diameter of your circle. And then the difference between how far the two are going gives you a ratio of your entire circle. And so by the time you're done, you just take a ratio of 360 degrees, or in this case, 6.28 radians. You can see right there, it's resetting at 6.28. So from that equation, your heading just immediately drops out and you've got what you need. Now that's how you do it for a differential drive or differential odometry. Now when we go to try to do odometry on the Ackerman steering, you have to take the distance from the motor in the back, how far you've gone, and then take from that you have to calculate how far it is from the back axle to the front axle, and then from that you have to look at what the angle of your wheels are pointed at, and you run all those calculations together, and that'll track. Basically, it's going to predict or calculate where your front end is based on the back end, and based on that, then you come up with a heading. So right here, I started looking at it, I think, well, that really looks terrible. I don't know why it's doing that, and I realized, oh yes, based on this, the fact that here one side's turning twice the speed as the other side. So what it was, because just a slight difference gives you an angle out of it. So in this case, let me zoom in a little farther than that. So in this case, is one side faster than the other one, it thinks, and it took me a while to realize it, but this number is just getting bigger and bigger and bigger. It's just that it's clipped at 6.28, so it hits 6.28 and drops back to 0. That's why it gives you that sawtooth pattern there. And then down here's where I sped the motor up, so it's just doing that much faster. So again, if we back up to that, look at it, see down here, see I'm running about twice as fast here as I was right there, and that's what this plot is showing you here. That down here it's just things that's going faster in circles. So I thought, well, how do I verify that? So I plotted my XY location that I got out of it, and sure enough, it thinks it's driving in circles. It's just driving around like that. So this is the other part of the odometry, where after you each time slice, in my case that's 1/10 of a second, you say how far did the left wheel go, how far did the right wheel go. From that you calculate the distance traveled, and the distance per time gives me the velocity, and that's what we were looking at before, is the velocity of the thing. But from that equation, it tells you how far you went in 1/10 of a second, and then the heading we just looked at tells you what angle you went in that 1/10 of a second. So you take it's like the sine of the heading times the distance plus x is your new x, and then you do the same thing for y, where y equals y plus cosine of the heading times the distance. And what that does, for each 1/10 of a second, it generates a new XY point here as you drive along in time. So as I came down here and when I thought it was driving in circles, sure enough, it thinks this is where the robot is. It thinks the robot's just sitting there driving in circles, even though it's sitting on my table, just driving with one side turning fast in there is what came out there. And I think that was the speed we looked at. There's fold stuff. That's what I had made. So.
How is that linked to the steering? So, like, I don't understand that piece of it. So the odometry, that makes complete sense what you're saying. But then, like, for instance, if your wheels are turned to the left or right, and then I guess there's the heading on the GPS, how does it know which one of those things is lying, like if your wheels are slipping?
Okay, right now I'm just looking at wheel odometry, and it turns out I can generate odometry from my 2 wheel encoders, and I can also generate odometry by taking the motor distance and the steering heading off the physical steering. So there's 2 different things going on here, and right now I'm just looking at the differential odometry like they use on the differential drive robots is what I'm using. So that's what I'm showing you right now. So then one of my next steps will be to figure out how to either get the value out of the RC servo to know the actual angle, or take the number I put into it where I had that plot. So right now the blue line I'm putting into it, I'm saying I want you to turn at that angle, and then this other stuff is coming back out of it. And it turns out that super servo is very sloppy. It's only good within it'll only track within like 10 degrees of what you tell it. So, but to start with, the easiest thing is I can just take the blue line here. It says, turn it like that, and we'll say that's 30 degrees. So if you know that your front wheels have turned 30 degrees, and then you know the distance between the back axle and the front axle, that tells you where that point is in space. So then if the wheels are turned 30 degrees and the motor says, I have moved 1 meter forward, then based on those calculations, you're basically calculating a new XY point for the back axle. So by the time I'm done, I should be able to get, if everything works right, the output from odometry 1 and output from odometry 2 should match. And I'm sure my steering on here, where the steering is goofy because of the way that super servo works, it's probably going to be pretty sloppy coming out. But right now, since it looks like I'm going to get fairly good stuff off my back wheels, off the actual wheel encoders, so I can go with that. Now back to your question about how do you know which one to trust? Well, that's yet a different topic, where say I have, where's an example here? Let's go back to.
Yeah, do you blend them with a filter of some sort, or?
Well, there's several things you can do, and people like to do that. And I keep warning people, don't trust exactly what they tell you to do, because they'll say, you should take an extended Kalman filter and feed in your wheel odometry and your GPS and your IMU and anything else you have and generate one number that's coming out. But at any point here, you can grab any one of these values because these are always being published as topics. So I can say, I can take my wheel odometry and take the Ackerman odometry, and I can directly compare those regardless of whatever else is going on. So I can watch the heading on both of those. And if those two are not agreeing, then that's a problem. I don't know, at that point, I don't know which one is wrong. I just know something's wrong at that point. And then likewise, if I'm bringing in my GPS, which goes off to this Kalman filter and is being used for all kinds of magic, well, I can take the heading off that and compare that. So now I have 3 different headings I can compare. So if 2 of them agree and the other one doesn't, I can say, well, the one that does not agree is a problem. And then likewise on heading, if I have an IMU on the system that tells me what direction I'm going or how fast I'm turning one way or the other, again, I can compare all those. So you could write a separate node that simply compares all the headings together and maybe have a node. It could be the same node or a separate one that's looking for the speed generated by the back wheel odometry and the speed generated by the motor encoder and the speed that's coming from the GPS. And I guess the IMU doesn't generate any speeds. So various things you can compare here. And even though the robot people say, oh, just feed in the Kalman filter and you're all set, just take whatever it tells you, believe that. Well, you don't have to do that. You can take all these different values and compare them yourself. So there's different ways you can do that.
Yeah, I'm just thinking it'd be nice to know if you were stuck or, something like that, because you could easily get a number out and not know that you're spinning wheels or stuck somehow.
Yeah, that's something that just came up the other day. I don't remember if it came up on Ross Agriculture or somewhere else. I saw that where somebody said, well, say you hooked onto a plow and you try driving forward and both wheels are spinning. That had never occurred to me that you could have both wheels spinning at the same time, that you're completely stuck. Because what I always see is you're driving along and say you get on ice or you get in mud or you hit a post or something and one wheel starts slipping on the back, just like in your car when you back before they had limited slip differentials, you're driving around in the winter and you get stuck and one tire spins and the other one doesn't do anything. That's what I have always seen, or that's what I've always assumed the problem would be, that the one side's turning, the other side's not. And what happens on that, I've got some plots from a long time ago, way back before Ross came out. I would drive my robot in my front yard, and if I drive my robot across the yard and look at the IMU output, actually, technically, I was just looking at the gyroscope output, and I could see if it varied one way or the other, and I could also look at the odometry. So what would happen is, if you start driving forward and I'm watching these 2 wheel encoders on the back, it will say, because I was also, at the time I had a differential drive robot. I had one motor on the left and one motor on the right, and I was actually controlling position. I wasn't controlling speed. And I said, okay, I want you to drive forward with this many counts per second on both motors. So you drive along, and if one motor starts slipping, the odometry thought, yep, no, we're going exactly straight, because the 2 wheels, the motors had enough power to keep the wheels turning, even though one wheel is spinning. Now the thing starts rotating sideways, and the odometry will say, no, we're going exactly straight. But you look at the gyroscope, as soon as you start to turn one way or the other, gyroscope tells on it real quick, says, oh, no, we're turning. So at that point, if you're comparing the heading from the odometry and the heading from the IMU, that instantly, and this was long before I had decent GPS, so I wasn't comparing that stuff at the time. But back to the point that it's not that hard to take all these different sensors and feed them into something. And the simplest thing is say, do they agree? And if not, then you can raise a flag and you can go look to see what to do about it. And then you could get real elaborate and then have some kind of a voting process that says, well, I think this one's right and this one's wrong, or these 3 are right, therefore this one has to be wrong. And actually that Kalman filter does that to some extent. It looks at all these different sensors, and if all of a sudden one of them's way off, it just ignores it and throws that out. I'm not sure it tells you that you've got a problem. It just simply starts ignoring things. And so if you're driving along and your GPS drops out, it'll just start ignoring that, and it'll just automatically switches to the IMU and the odometry to generate your path. So there's various ways around that. And I think it's going to turn out to be a whole topic about, how do you how do you read these, and how do you know whether to trust them or not? But right now I'm just trying to get the low level stuff where I can, get the information out. Because my next step is, when I did this, I went through and said, okay, here's the approximate diameter of my tires. Here's my approximate gear ratio. I said it was 18-1, but it's actually like 17.35 or something, what it said on a data sheet. So what you have to do is, once you put it all together, you make these rough calculations. And I said that looks like it's going 1.5 meters per second. That's going to be an approximate number, but I have to now actually take it outside and put it on the ground and drive some distance, say drive 10 meters and go measure that. But first of all, get a tape measure and put 10-meter mark on the ground, and then take the vehicle and put it at the beginning and reset the value and drive it forward and stop on the mark and say, does that equal, do the two numbers match? Because I end up with a scale factor in here. So when I have a scale factor that says number of counts per meter for driving. And I said I had 43,200 counts per revolution of the wheel. That's also an approximate number because I'm not sure about my gear ratio. And I said it's approximately 1 meter distance traveled per revolution of the back wheel. And again, that was kind of a judgment, just kind of a quick way to get around this stuff. So I have to go calibrate all that stuff and know exactly, if I drive exactly 1 meter forward, how many counts is that actually? Instead of being the 43,200, it's going to be some other number higher or lower than that. And then likewise, when you go to the steering, you have to make sure that if you drive in a full circle, you have to make sure that the scale factor is set so that comes out right also. So right now I'm just in the process of trying to do all these low level type things so I get the right kind of values coming out. And at this point, I don't even know if I start driving forward and start turning left, if it's smart enough that I'm turning left instead of right. And then also a number that falls out of the odometry equations is your rotational rate. So it puts out a number that says your vehicle is turning left at so many radians per second. And that's just simply take the current heading of the last heading, subtract the two, and divide that by your time slice. And that tells you how many radians per second you're turning. So that's another, I got to make sure all those numbers come out right. So there's just some time sitting down trying to calibrate this out and figuring out what the proper scale factors are for all that. And since I'll have one scale factor for my wheel odometry and another scale factor for my Ackerman odometry, that's going to be something I have to adjust both of those separately. And then once I get my RTK GPS running, now you can automate some of this stuff. You say, kind of point in that direction. There's nothing in the way. Reset your location to 0, and then whatever your RTK comes in, so you set that one to 0. So if you're taking your latitude and longitude and comparing that to whatever your known location is, and then you're going to call it 0, 0. So you're creating an origin wherever you're sitting. So if I point my robot in some particular direction and then say reset my encoder counter and reset the origin for the GPS, they're both going to say 0. And if I just drive forward some arbitrary amount and come to a stop, then I can just read the distance that the GPS thinks it went and read the distance the encoder thinks it went. And those two are probably not going to be exactly the same, but now I can take the ratio of those and put that back into the scale factor for the odometry. So at this point, I would trust the GPS because, I paid a lot of money for it, and that's the whole point of it, is to tell me within a couple of centimeters how far I went. So the farther you drive, the less significant that little bit of GPS error is. So number one, I could do some kind of automatic calibration where you drive a certain distance and then calibrate your distance. And then also you can then say, turn the wheel all the way left and drive until you go to full circle. And then go back and look at your numbers from the RTK GPS and say, the diameter of the circle was this, and I predicted it should have been this. So that's another scale factor you can come up with there. So there's all kinds of little things that, in the next day or two, I won't get all this done, but that's where I'm headed, is to come up with that kind of stuff.
Yeah, that'd be neat to have some type of thing, because then it'd make the system portable. I was thinking while you were talking about the calibration piece, you definitely need to be not, I don't know how to say it, not live or live. Like I can think as a practical matter, like when you're pulling something, that the wheel slips a lot of time is continuous. So, and it's not always the same, because if the implement's like in the ground further, out of the ground further, obviously for a lawn tractor, it's one thing, but like actually pulling an implement. So it would lie to you different amounts, right, based on the wheel slip. So like, but if you weren't under load for your calibration phase, like what you're talking about, then that would work pretty neat to get this set up and get a really good estimate without doing any typing numbers in or anything.
Yeah, I want to bring up one point here that I said this is how you can do calibration. The other thing is good that every day you start up, have it run through some kind of test and just say, are within a couple of percent of where we were yesterday. So it's just a verification to make sure all of your different sensors are working correctly. And if any of them are way out, you know you've got a problem. And if they're off by say maybe 5%, you can just go ahead and load those new numbers as your new calibration values. But back to your point you just made about as you're driving and you get constant slippage, as an operator, what do you do about that? So you're driving down your field plowing and your tires are slipping. Do you either slow down or do you make any corrections for that, or are you just aware of the fact that it does that?
I mean, sometimes it just has to be that way. But sometimes like you could raise the implement a little bit or add suitcase weights to the tractor, those sorts of things. But yeah, most of the time there's just some level of slip that exists. Also, like if a field is wet in certain locations and it's dry in other locations because it's not, it's a piece of ground. So you just have to deal with that, where you go through a wet spot and the tires will slip a little bit. No
Yeah,
big deal.
as far as adding weights, that's something you'd have to physically stop and get the weights and put them on. Whereas I can see if you just raise your implement up so it's doesn't have as much bite, I suppose you could do that on the fly. So it might be a matter of the numbers coming out tell you that, well, it is slipping. So it might just give you a number coming out that tells you it's slipping. But still, if you're trusting your RTK GPS at that point, you just simply know that's the speed that you actually want to go by. So there's various things there that would need to be, somebody just needs to think about all the stuff and decide what to do about it in the different cases.
Yeah, I can give you a couple of practical examples that might just be interesting to think about. So some tracked vehicles don't have positive drive to their tracks, meaning that the track tension's what locks the drive roller to the track. And so, for instance, I've been in situations where the track gets wet and the drive actually slips inside the track to a certain degree. It can be like excessive sometimes even, but so there's a chance for what you would consider traction loss there, but it's not actually spinning the track on the ground, if that makes sense. Um, there's also the vehicle the tractor will, when it's under load from being pulled, especially if you're on like a side hill or something, if you get on real wet ground, the vehicle actually slides sideways as opposed to, straight forward because of the way that the torque is on the rear hitch versus the hillside. So there's all sorts of things, scenarios like that you run into, practically, that you kind of don't plan to happen when you're writing the software piece of it. And it all revolves around like looking at the slip basically of the, I would trust the GPS, right? And then you kind of know how wrong things are going based off the slip. So yeah, just a couple thoughts there.
So basically, in a situation like that, you have to steer up the hill as you drive forward. So you're constantly
Yeah,
constantly driving at an angle as you go.
yeah, you have to steer up the hill to correct it. Absolutely. Or sometimes there is no like great correction. So for instance, the sprayers, if it's going up a hill and say it slides off course, 6-8 inches to the right or left, it corrects, and then it's kind of a an underdamped system at that point. It tries to weave around the imaginary line that's cut across the field to refine its position, and sometimes that means the vehicle's like kind of spinning, going sideways. You can imagine like burning out in a vehicle and trying to correct the steering by over or under steering. But it's all, it's all live. The vehicle's going. You don't stop and try to correct it or something like that. And there is no, I don't know how to say it. There's no exactly correct number. There's only the correct number for that instance of time where it should try to shoot. So, yeah, it's good numbers to have broke out, because then I'm sure you can do a lot of things. And it matters what type of vehicle it is too. A four-wheel drive tractor acts different from a tractor, acts different from a hydrostatic drive sprayer or hydrostatic drive tractor like a TV 6070. So they're all kind of different.
So yeah, your point is it's going to come down to tuning for each vehicle. You're going to have to, see how it acts and how to, how to correct for that. Maybe you detect it the same on all of them, but then, for like we're talking about, you might have to drive up the hill, or if it's a tracked vehicle, you might have to do something different depending on what it is. So.
Yeah. And a lot of tractors have ground radar in them to actually measure wheel slip, because they have their internal odometry. Even older, a lot of older tractors like 80s tractors will have a late 80s, I guess, would have odometry in them, and like a ground radar that just says what the percentage of wheel slip is, like as a continuous feedback to the operator.
Okay. That pretty well sums up everything I had to say, I guess. I'm done babbling on now, so I'll turn it back over to whoever wants to go next.
That's a lot of progress.
Yeah, pretty cool.
Al, I don't know if you want to give us an update on your progress.
Sure, I'll share a few things. So let me get sharing turned on there. I was looking at that tachometer. Thanks for sharing that. So in the Slack channel, this is what you're looking at is the front angle sensor that I've got on my lawn tractor. Same basic model that Matt has got as far as the tractor goes. But I moved the angle sensor out over this pivot point because I had installed it on the gear that is driving the steering linkage, and I found movement in that, so I had to find another alternative, and chose to go here, a little bit of a better picture here on that. And so my status at the moment is programming the PID controller for the steer angle motor, or for the steering motor. But that's the sensor that I've got. Let's see what I've got here. So I've effectively got two programs to manipulate the situation. One is the code that runs on the teensy that's sitting out over the angle sensor, and then there's another teensy that's driving the steering control module. So the function of the teensy out over the angle sensor is, as you might get, to publish the angle. I happen to be publishing 2 or 3 versions of that just to see the different data. One is just the raw angle. I've got the sensor, which is an I2C sensor, running at, let's see, oh, I'm sorry, I need to look at someplace else in my code. So I'm using the teensy timer and firing that timer at 20 hertz, which is effectively then going out to the I2C sensor and grabbing that data. So publishing that just raw data is one of the things that I'm publishing. As Jeff had mentioned earlier, I am feeding that through a Kalman filter. It happens to be the simple Kalman filter that's at that GitHub site. And so that's effectively the function of that, you know, the teensy that's sitting out over the angle or out over the front axle. And then the second program that's running is the steering control module that's driving the steering motor. And it, as you would guess, is subscribing to the front angle value, and it's subscribing to command velocity, and it's publishing the target because I wanted to plot, you know, actual and target so I could adjust my PID settings. So at the moment, that's where I'm at. Is this is all working, and this is code that I borrowed from Matt and started with his base code, and at the moment it just has an integral value, and I was starting the testing process of what does that actual versus target look like, and adjusting that integral value. So that's where I'm at, and then it publishes, you know, some messages down here just to let me know what's going on. This code, by the way, is out on Google Drive out there. So if you want to look at it in any more detail, it's out on the Google Drive. And that website is right there. Get back to the chat, maybe, if I can figure that out. Where's the chat?
Is there another package that helps automatically tune the PID values?
You know, I was looking at, I don't know is the answer to your question. Matt had mentioned Lino Robot, and I was looking at that and trying to make some sense out of whether I could make that work or not. And there were a couple of packages that I needed to install. It happened to be for Indigo, and I was getting some error messages. So it didn't look like it was an automatic adjustment, but it looked like that they had created I'm not familiar enough with RQT plot, but they had created a perspective file, and in that perspective file, it had some slider bars for all three of the, you know, the PID settings. So it wasn't an auto. The Lino Robot thing was an auto tuning, but it was certainly a useful user interface to help tune the PID.
Yeah, sometimes it can be interesting to tune, I guess. It'd be interesting if there was a package that sort of gave you a best guess.
Yeah, I actually was just going to try to write a script, a Python script probably, to feed in some standard positions, calculate the area under the curve, and sort of mathematically, you know, quickly get to what is mathematically producing the lowest area under the curve, and working my way through that. But, you know, maybe I should just do it by feel instead of trying to do it programmatic.
Yeah, it looks like MathWorks for MATLAB has a PID tune. If you have access to MATLAB, I don't know if Octave also has, you know, depending on what the data set looks like. I'll throw a link in the channel. But
Yeah,
if
thanks
you
for that.
get the data link out, then it might be worth taking a look at.
So I'm getting pretty close to being able to drive mine around with the joystick, but so making slow progress, but inch by inch.
Awesome, Al. Is there anybody else that has a project or an update?
I don't have any updates myself. I wish I did. So last couple weeks have been hectic, but the more I sit in on these meetings, it's super useful to hear what everybody's doing and kind of get a handle, get my head wrapped around what I want to kind of do after some of my initial things. It seems like you guys have tried a lot of stuff to get bootstrapped on some of these topics.
It's always a learning game. I've been trying to get a plant inside of Gazebo, a lifelike plant, and now I'm learning how to use Blender. You just never know where you end up when you want to work with robots, what you're going to be learning next.
Yeah, I did actually try to generate a terrain model for Gazebo. Did any of you guys have any luck with that Python script that's out there? You know what I'm talking about?
No,
Ye-
like height maps.
Yeah, exactly. Yeah, I was trying to grab Google Maps data for a field like in a 8K by 8K square or something, and then dump that into Gazebo and then view it by either just grayscale or color. And for some reason, the 8K by 8K, when I say K, I mean kilometer,
That's huge.
size map came out smaller than what the gazebo did for the example. So something was scaled completely wrong. I didn't know if anybody's had any luck generating a actual sizable terrain map to play around with.
I haven't done one from like a DEM from like Google Maps, but I've made the height maps for terrain.
And where did you get the height map data from?
I made it up.
Okay. Yeah, I thought it would be nice to get a couple of the fields that have terraces in them and actually generate a height map so I could, see how things might act eventually on non-flat, um, non-flat ground, I guess we'll say. We were talking about vehicle terrain compensation, the not last meeting, but the previous one. And that's one of the issues is you go over a terrace and your GPS flies, 4 feet to the left when you roll over the terrace and then 4 feet to the right when you roll over the other side. And so I assume that if you have a height map that you can sort of see how those things act before you commit any time to actually driving around in the vehicle with it. But so that was my little bit of time that I had to stick into it. Well, but it didn't work yet. So I guess I'll give you an update when it does.
That's cool. I'm still learning how to use Gazebo. It's neat, but takes a little bit of time, change of thinking. Well, great. Looks like we're at the top of the hour. Thanks for being here. It was interesting, and hope you guys make good progress on your robots this week.
Thanks, Matt.
Thanks, guys. Talk to you guys later.